Hello! So if you remember, last week we were talking about linear systems of equations with n unknowns in, and we looked at Gaussian elimination as a method to solve that system of linear equations. Okay. We also looked at a few adaptations of Gaussian elimination, such as partial pivoting and LU decomposition. But what we didn't really have a lot of time to think about was what the cost of Gaussian elimination is. Now, cost is really important when it comes to trying to solve things using a computer, because clearly we want it to solve things as quickly as possible and as efficiently as possible. In other words, we don't want to be sitting there for a long time waiting for it to solve this system of linear equations, right? Because we might have other systems of linear equations to be getting on with, or we might want to use our computer for other things as well. So if we go through and if we think about all of the different processes that are needed to solve something using Gaussian elimination, such as finding the pivots, the multipliers, how to add or subtract one row from the other, also the number of steps that are required, we find that Gaussian elimination comes out on the order of n cubed, where n is the number of unknowns that we're trying to solve. But what does this mean? Well, okay, let's suppose that I code Gaussian elimination up in something like MATLAB, and I time how long it takes for my particular code on my particular computer to solve a system of 10 linear equations, okay, with 10 unknowns in, obviously. And I find that it takes 1 millisecond to solve. Now, you might be sitting there saying, yeah, do you know what? That's pretty good. I'm pretty happy with that. However, we have an issue because my Gaussian elimination works on the order of n cubed. It's got a cost of n cubed. Then it means that as I increase the number of equations, this time does not increase linearly. In fact, it increases using n cubed instead. So to illustrate this, let's actually think about this in terms of a table. So down here I've got a table where the first column is the number of unknowns, and the right column is how long I expect my computer to take to compute this many unknowns. So, okay, with 10 unknowns, I find that it takes 1 millisecond, okay? With 100 unknowns, well, okay, I'm going to basically increase this 1 millisecond by 10 cubed times that. In other words, it's going to come out as 1 second, okay? Now, you might be sitting there thinking, yeah, do you know what? That's pretty good. I'm quite happy with that. But what happens if we increase it to 1,000 next? Well, if we increase it to 1,000, we find it comes out on the order of 17 minutes. Now again, you might be sitting there thinking, well, okay, that's not ideal, but at least I can go off and get some lunch or something to try and do something whilst this computer is solving it. But as I increase it even more, maybe to 10,000 unknowns, then it's going to take nearly 12 days in order for my computer to solve that system of equations. And just to illustrate my point, with 100,000 unknowns, and that is not unheard of actually, with 100,000 unknowns, for my computer to solve that many equations with 100,000 unknowns, I am expecting it's going to take in the region of 32 years. Now clearly, I'm not going to be waiting until my 50s in order to solve this system of linear equations. I'm really not that bothered, okay? So in other words, the moral of the story is, Gaussian elimination is great, however, with large systems of equations, it becomes very computationally expensive in terms of time. However, there's also another issue which I have to contend with as well. It's that as I increase the number of unknowns in my system, very rarely do I ever have equations formed with every single unknowns in, okay? In other words, that means that when I'm storing my matrix in a computer, I don't have to store every single element in there. For example, if you take this top matrix, I would describe that top matrix as very dense, on the basis that pretty much every coefficient of my 5 unknowns is non-zero. Okay? In other words, I'm going to have to store all of these numbers in my computer. And that, depending on the size of the matrix, could take up a lot of space. For example, it might take a gigabyte worth of space to store a very big matrix in. So the way which we get around that, for example, if we have a sparse matrix, in other words, we have a lot of equations formed, but very few of those equations have every single unknown with a coefficient. In other words, there's a lot of zeros in my particular matrix. I would call that sparse. Now that's really useful from the perspective of being able to store large matrices in a computer, because what we tend to do is just go through, pick out the non-zero elements and basically just store those elements with their positions in the matrix. Rather than storing every single element, we just store the non-zero elements, which there are far fewer of, and their positions. However, when we apply Gaussian elimination to this sparse matrix, we have an issue. Because if I just demonstrate with this matrix down here, and I know this is not a particularly big matrix, but my point is there are some zeros in this matrix. When I perform Gaussian elimination on this particular matrix here, after the first step, I basically turn some of those zero elements into non-zero elements. In fact, this is the Gaussian elimination matrix after that first step. So hopefully you can see that, for example, this element here, which was zero, so in other words, I would be not storing that element in my method of storage because it may be a sparse matrix, so I just store the non-zero elements. But the issue is, using Gaussian elimination, that particular element has changed to a non-zero element, which means I've got issues with the way I now need to store that new matrix, because I need to now update it with a new element, and I also need to update it with the position at which that element is stored in, okay? So this particular method, or the particular issue which we've got here, is that my matrix is being filled in. In other words, some of those zeros, there's a lot of zeros in my sparse matrix, end up being filled in with non-zero elements when I do my Gaussian elimination step. So that's another issue with my storage. So it's not just an issue for Gaussian elimination with a large number of equations and a large number of unknowns. It's not just an issue with respect to time, but it's also an issue with respect to how I'm storing my matrices in there. Because I basically turn a very sparse matrix into a dense matrix when I'm using Gaussian elimination. So I need to come up with a better method, and this is where my iterative methods come in.